I welcome you all for this lecture series on 4G and 5G communication networks. In this lecture number 18, we will briefly discuss about the concepts of multi-access edge computing, that is MEC in 5G. This multi-access edge computing in 5G enables cloud computing capabilities and IT services at the network edge closer to users. It reduces latency, enhances data processing, and improve real-time application performance. MEC supports various 5G use cases like, as I have said many times, autonomous vehicles, IoT, and AR, VR. By offloading tasks from centralized clouds, MEC optimizes network efficiency and user experience. Next, we'll see the introduction about the multi-access edge computing, that is MEC. Multi-access edge computing is a crucial component of the 5G ecosystem designed to enhance user experience by bringing application-oriented capabilities closer to end users. By positioning computing resources at the edge of network, MEC significantly optimizes performance for latency sensitive applications, ensuring ultra low latency and high bandwidth services. Initially referred to as mobile edge computing, its scope was primarily focused on mobile networks. However, the industry has recognized its broader applicability across both wireless and wired networks, leading to its rebranding as multi-access edge computing. This evolution underscores MEC versatility in meeting the demands of a wide range of applications in today's digital landscape. Next, we'll see the need for multi-access edge computing. So in the previous generations of mobile networks such as 4G and 3G, compute infrastructure for application services, including functions like video transcoding, WAN optimization, and content delivery networks, was primarily located within the service provider's core network. However, as the number of mobile devices connecting to these networks has increased significantly, alongside a dramatic rise in data consumption, relying solely on centralized services has become impractical. The latency and bandwidth limitations inherent in this centralized approach can lead to degraded user experiences, prompting the need for a more efficient solution. Next, key drivers for MEC in 5G. One of the primary drivers for adoption of multi-access computing in 5G network is the explosive growth in the number of mobile devices, particularly due to the Internet of Things, that is IoT. This surge in connectivity demands necessitates a more responsive infrastructure capable of handling vast number of simultaneous connections. Additionally, the volume of data generated by over the top, that we can call it as OTT applications such as social media platforms, video streaming services, and online gaming continues to rise exponentially. This growth not only stresses existing network resources but also highlights the need for localized processing to deliver seamless and high quality user experiences, making MEC an essential component of modern network architecture. Next, the distribution of infrastructure is a critical driver for multi-access edge computing in 5G, as hosting application services closer to user significantly. It improves performances and enhances the overall user experience. By minimizing the distance the data must travel, MEC, what it will do? It will reduces the latency and allows the faster response times. which is essential for applications that require real-time processing. Additionally, running application services in multiple geographic locations enhances service reliability as it mitigates the risk of service interruptions and ensures continuous availability even if one location experiences it makes it an issue. Moreover, service virtualization plays a vital role in MEC by reducing the dependency on specialized purpose-built hardware. This flexibility simplifies the management and orchestration of service across multi-vendor environment and enabling operations to deploy a variety of applications more efficiently. And finally, one of the most compelling advantage of MEC is its ability to dramatically lower network latency. This reduction is crucial for supporting innovative use cases such as autonomous cars, virtual reality, and augmented reality and robotic surgeries, all of which demand extremely low latency for optimal performance and safety. Together, these factors illustrate why MEC is an essential component of the 5G landscape. And this is the MEC architecture. It consists of various parts: visualization, infrastructure. This is application part, service part. This is the MEC platform, and it consists of MEC orchestration, MEC platform manager, and a virtual infrastructure manager. We'll see one by one. The architecture of multi-access edge computing is designed to closely resemble network functions virtualization, that is NFV architecture, which facilitates efficient resource management and service delivery. By adopting virtualization technologies, MEC can optimize the deployment of applications and services at the edge of network, thereby enhancing performance and responsiveness. This structure supports a flexible and scalable approach to managing the increasing demands of modern applications, particularly in the context of 5G networks. And some of the key functions we'll see. The first one is the MEC orchestrator. The MEC orchestrator plays a critical role in managing and coordinating the various components within the MEC environment. It ensures that resources are efficiently allocated and that applications can seamlessly interact with one another. By overseeing the orchestration of services and applications, this function enhances the overall operational efficiency and responsiveness of MEC architecture, making it easier for service providers to deploy and manage edge applications effectively. Next, MEC Platform Manager. This MEC platform serves as the foundation environment for deploying and executing MEC applications. It provides the necessary infrastructure and services to facilitate application development and deployment at the edge. By offering a standardized platform, it enables developers to create applications that can adopt edge computing capabilities, thus ensuring compatibility and ease of integration with various network components. This platform is essential for driving innovation in edge computing. Next, MEC Platform Manager. This MEC Platform Manager is responsible for overseeing the operational aspects of MEC platform. This includes managing resource allocation, monitoring performance, and ensuring service quality. By actively managing the platform, the MEC Platform Manager can dynamically allocate resources based on demand, optimize application performance, and maintain high availability. This function is vital for ensuring the MEC environment operates smoothly and meets the needs of users and applications. Next, virtualization infrastructure. This virtualization infrastructure underpins the MEC architecture by supporting virtualization of both network resources and application services. This flexibility allows for efficient deployment of applications in various environments without being tied to specific hardware. This is the main advantage. By abstracting physical resources, the virtualization infrastructure enables service providers to scale their offerings rapidly and adapt to changing demands. This capability is crucial for optimizing resource utilization and delivering high performance services at the edge. Next, MEC application services. This MEC application services are the core offerings that utilize the edge computing capabilities provided by the MEC architecture. These services host various applications designed to deliver low latency and high performance experiences for users. By operating closer to the end user, MEC application services can process data in real time, enabling innovative applications such as augmented reality, autonomous driving, and smart city solutions. This function is essential for realizing the full potential of edge computing and meeting the evolving needs of users and industries. Next, MEC deployment modes. So there are four modes are available in MEC deployment: breakout mode, inline mode, tap mode, independent mode. We'll see one by one. In this mode, in the breakout mode, the session is redirected to MEC application, either hosted locally on the MEC platform or on remote server. This is often used for applications like local CDN caches and see here coming gaming services or media delivery platform like Netflix. Traffic is stored by defining forwarding policies. In the next mode, inline mode, the MEC is deployed transparently where the session connection remains within the original server. However, the traffic passes through the MEC application. This is used for scenarios like transparent content catching or security applications. Next one is the tap mode. In this mode, session data is selectively duplicated and forwarded to MEC application. It is commonly used for virtual network probes, monitoring, or security applications where duplicating the traffic helps gather data without interpreting the original flow. Next, independent modes. In independent mode, the MEC applications run separately but are still registered on the MEC platform. These applications can still receive MEC services like DNS and radio network, the DNS and radio network information. Traffic steering is managed through DNS configuration or the MEC host data plan. Next, MEC deployment scenarios in 5G. This multi-access edge computing can be deployed in several locations, ranging from close proximity to base station to the central data network. Regardless of MEC is placed, the user plane function, that is called UPF, plays a crucial role by steering the traffic towards the MEC applications and back to the network. The flexible nature of 5G architecture allows UPF instances to be deployed both at edge and at the core of network, depending on the specific requirements. This flexibility helps improve network performance by reducing latency and enhancing overall service delivery, particularly for applications demanding low latency and high bandwidth connections. Next, the key factors affecting MEC deployment in 5G. When deploying MEC, that is multi-access edge computing in a 5G network, several key factors must be considered. First, infrastructure availability, including power, space, and cooling, is essential to ensure that necessary physical resources are in place to support the deployment. Next, the type of application or services hosted in MEC also plays a critical role as different applications may have varying computational and storage requirements. Additionally, network latency requirements must be met particularly for real-time applications that demand minimal delay in communication. Next, lastly, the bandwidth requirement. The bandwidth requirements determine how much data the network needs to handle efficiently, which directly impacts the performance of applications hosted on MEC. These factors collectively influence the placement and efficiency of MEC within a 5G network. Next, MEC deployment scenarios in 5G network. Thus, in 5G, MEC can be deployed in various scenarios, each offering unique benefits. When MEC and user plane function UPF are co-located with the base station, this setup ensures ultra-low latency, making it ideal for real-time applications such as augmented reality, online gaming, autonomous driving. On the other hand, when MEC is co-located with a transmission node, possibly along with UPF, it is particularly useful for regional traffic aggregation. This deployment can improve network efficiency and reduce the distance data needs to travel, optimizing bandwidth usage for localized services while maintaining good performance levels. Next, integrating MEC with 5G networks. Integrating MEC with the 5G network involves several key components that enhance the network's capabilities and performance. MEC services and applications can act as application functions, that is AF, we can call it as AFs, which allow them to consume and utilize information exposed by 5G network, such as user mobility and location updates. This enables application to be more responsive and adapted to user-specific data. Local routing and traffic enables selective traffic routing to local MEC applications for optimized performances. And if you are considering application functions and policy control, AF influence user plane function, as I've said, selection via policy control function or a network exposure function. And it administrates the administrators define forwarding and redirection rules in PCF or NEF APIs, streamlining 5G core access. And MEC local area data networks. So MEC apps can connect LADN in the 5G core for localized services. Example, stadium streaming for on-site users. And what are the challenges? The challenges of UE and application mobility. However, the application mobility presenter, that is a UE and application mobility present challenges for mobile users or devices like autonomous vehicle. Continuous motion can result in fluctuating response time if they move away from the MEC host. So this usually will happen. In these cases, the session must be seamlessly migrated to another MEC host closer to users. If the application is stateful, synchronization of session data across MEC instances is required. If the application is stateless, session migration is simpler as no data synchronization is necessary. And MEC use cases in 5G network. MEC for enterprise services. It enables local hosting of corporate applications for enhanced security. It is ideal for industries like healthcare and government, supporting ultra low latency applications such as live streaming and robotic surgeries. And this MEC for IoT services, that is Internet of Things services. It facilitates edge computing for IoT application, allowing local data collection and analysis. It enhances reliability and responsiveness for IoT monitoring services. Next, MEC for third-party services. How it will be used for third-party services. Finally, the third-party services can adopt MEC by positioning applications like video optimization and CDN caches closer to users, effectively addressing latency requirements and creating monetization opportunities for service providers through partnership and revenue sharing agreements. Next, benefits of MEC. The MEC offers several benefits, including support for low latencies in 5G networks, which enhances application performance and user experiences. It enables service providers to experiment with new customer facing services without significantly disrupting their network. Additionally, MEC increases monetization opportunities by facilitating new network services beyond traditional connectivity and allows over the top, I have said OTT application to adopt wireless customer information for customized experiences. It enhances security for IoT services by distributing the attack surface and improve the reliability of applications and network services through the distributed infrastructure for failover. MEC also provides real-time access to data locally in IoT environment. See here, IoT facilitates local policy management for enterprise customers and reduces operational costs by minimizing need for expensive data centers. And finally, coming into the conclusion, multi-access edge computing enhances latency and performance by processing data closer to users, which leads to faster response times. It optimizes resources by reducing bandwidth consumption through offloading data processing to edge services. MEC also supports the connectivity needs of IoT devices and meets the demands of 5G networks. Overall, it improves user experience in applications like augmented reality and smart cities, enabling innovation services and solutions. Hope everyone enjoyed about this lecture on MEC. The remaining things we'll discuss in the next lecture. Thank you.